Hi, I am Esteban Aguilar and this is my Physics 2211 Lab 4 Oscillations. The purpose of this lab is to compare the predicted motion and the observed motion of a mass oscillating in a spring in both the x and y directions through a computational model. In addition, I will plot the energy changes that I compute in the model. The physics principles I will be using include Newton's second law, which tells us how the net force is equal to a change of momentum over a change of time, which gives us the velocity update formula. I will also be using the position update formula. Some forces I will be working with are gravity and the spring force, whose formulas appear on the slide. Finally, I will be using the energy principle, which states that the change of the energy of a system is equal to the work done by the surroundings plus the heat transfer. As a quick preview of the lab, I have found that the computational model predicts the mass motion fairly accurately. This is a diagram of the experiment. Here, there is a spring where one of its ends is fixed while the other has a mass on it. Initially, the mass is moved slightly before being let go, and experiences both gravity and a spring force, which are reflected in the arrows in the diagram. Here, the system is the mass, which is 0.402 kilograms. The spring, with an initial length of 0.123 meters and a spring constant of 6.83 newtons per meter, and the Earth. On the other hand, the surroundings are everything else. This is a screenshot of the video of the observed motion. I use Tracker to measure the mass position of each frame. These are the initial conditions of my computational model. Here I added the mass and, using Tracker, I found the initial position vector, which is negative 0.113, negative 0.6419, 0 meters, and the initial velocity vector, which is 0.0015, negative 0.001, 0 meters per second. Tracker also gave us a time between frames, which was 0.095 seconds, which I added as delta t. In addition, I added the constants of the spring mentioned in the diagram. Finally, I added the formulas of the energies that will be relevant to my experiment, which include the kinetic energy, the gravitational potential energy, the spring potential energy, and the total energy. This is the loop of my computational model, which will work while the time is less than 9.5 seconds, since this is how long the video is. Then I stated the initial energies as well as the forces relevant for the experiment with their respective formulas. Afterwards, I used the velocity update formula and the position update formula to continue updating the computational model. Finally, I found the changes in the energies by subtracting the original energies from their current values. This is a screenshot of the predicted motion alongside the observed motion. We can see that the computational model created predicts fairly well the observed motion, especially in the beginning. However, as time passes, the x position go out of phase, and the amplitude of the y position of the model decreases. This can be seen in the two pictures on this slide. Also, as shown in this graph, which shows a change of energy versus time, the total change of energy is always zero. However, the changes in each individual energy are not zero as they oscillate. Some possible sources of error are possible inaccuracies while using Tracker, the fact that the spring is not ideal, only considering two dimensions and not considering air resistance. The first additional question is whether the energy principle is satisfied. The energy principle is satisfied since the change of energy of the system is equal to the work done by the surroundings, plus the heat transfer. This is because there are no external forces, which means that the work done by the surroundings is zero, and there is no heat transfer. So since both of these values are zero, the change of energy of the system should be zero, which is the case as reflected in that graph. The second additional question asks us to estimate the period of oscillation from the x position and the y position. In the x position, 5 oscillations are done in 8.2 seconds, which gives us a period of 1.64 seconds, while in the y position, 6 oscillations are done in 9.1 seconds, which gives us a period of 1.52 seconds. As a conclusion, I can say that the computational model created predicts fairly well the observed motion, especially in the beginning. However, the observed and predicted positions diverge as time passes, which could be explained by aspects such as air resistance, which were not considered in this computational model. Thanks for your time.